All right, I will hit record to officially start. So what I had not recorded is reminding folks of the schedule. Inside icon is the list of who is presenting when and who is peer reviewing those presentations. Make sure you take a look at that, and we're all on the same page as to what is happening. All right, so this handout looks different. As you can see, this is not Lisa's quintessential syntax output style. This is an R Markdown document that I made, and so I'm very proud of myself for having to do that. I thank Vladimir for his help, also Jonathan for his help in giving me things.
Yeah, I'll just bow to anybody who can do that. Could I try?
It's actually not that bad. It's not as bad as I feared. Once you get used to the weird little punctuation, like this tick, this bar, this apostrophe-looking syntax, which I've never seen elsewhere, that was the thing that I got the most wrong. It's like, oh, that's not an apostrophe. That's a different symbol. But anywho, where this handout came from and why it looks different is that this is a data set that I've used in examples in coursework across multiple years for various purposes. This one is from a workshop that I gave in the summer of 2024 to a group of students that I've been aligned with in Germany for the past couple of years. So there's a consortium of psychology departments in German universities that had a training grant, essentially to expand their methods focus, and I was brought in as a Mercator Fellow to help them do that. So yeah, I have a fancy title. And I gave this workshop on Zoom. So those students only use R because that's it. So I only made this in R. However, since I had to make it work for this package, you will see Stata code just shoved in here randomly. So I have a complete reporting of that. But the Stata models actually did not run after about the second or third iteration in this handout, so there's not a lot to report there. Stata's not good at cross models, but would you like to hear the backstory of the story?
Yeah.
It's a true story. Why not?
True stories are great.
Yeah. So these data come from somebody that I went to graduate school with, Larry Locker. There's a publication linked here. So Jim Bovaird was also someone I went to graduate school with. And there was one evening, I think it was a Friday evening, we were like having pizza, shooting pool, group of grad students decided to go out. And Larry is really bummed because his paper had gotten rejected from a journal. And we asked him what happened, and he said, well, my F1 ANOVA was significant, but my F2 ANOVA wasn't significant. And at that point, I was pretty well acquainted with ANOVA, so I said, what the hell's an F2 ANOVA? Like, I've never heard this before. So he explains. So in Larry's world, he does psycholinguistics. So he studies things like how quickly people respond to pint versus pint, or like whether words that have more associations are detected or responded to faster, like these kinds of, it's like the intersection of linguistics and psychology, psycholinguistics. I know very little about this. We're going to have two predictors, and they're both going to be low and high of something. Okay, so if you want to know more details than that, you can ask psycholinguistics people. But in his case, what he typically does is recruit psychology undergraduates to respond as quickly as possible to decide if a given stimulus is an actual word in English or a non-word. Yes, the airplane is back, thank goodness. I get to yell louder, that's even better for me. So in this example, this is from the failed paper that got rejected. Actually, it's from a different study that's very similar to the failed paper. The reason the paper got rejected is tied to the story. 39 items from 38 subjects in this case. So there was a tradition in this field, I think it has since died out, which is a good thing, that in these types of designs, you would do two complementary sets of analyses. So he has 4 different kinds of words that he manipulated in a 2x2 design. So the F1 ANOVA, as it is called, would aggregate the responses from the same cell into a cell mean for each person. So you would have 4 cell means, essentially corresponding to the 2x2, and you throw that into a repeated measures ANOVA. Subjects would be the random factor. The design conditions are treated as fixed. The trials are treated as exchangeable. So in this case, he would have pretty good power to do that with 36 subjects, or to do the opposite. So if you think about items as the unit of analysis, then you would aggregate all the responses across subjects for each item. Item would be like the rows in the data set. And then the F2 ANOVA would be between subjects, because subjects are the items at that point. Okay. So one focuses on what is the impact of item things, and the other focuses what's on the impact of person things.
Cool.
Well, neither one is right. That's the problem. Because if you aggregate over items in the same condition, what you're saying is that you have perfectly controlled for all the reasons those items would still differ from each other within the same cell. And if you're dealing with real words, that's very difficult to do. The opposite then would pretend that all subjects are exchangeable, right? All people are the same. We can just take an average across all of us and call it good, and that'll generalize to other samples, right? So that's not cool either. So it turned out that in the paper that Larry got rejected, F1 ANOVA had about 120 subjects or something to power it, because in psychology, we're always focused on power, thinking about subjects. We just need more people. But he only had something like 15 items in that example. So power across 15 is going to be terrible. So it is completely unsurprising that his F2 result did not mirror his F1 result, because they're both using a different type of error as what the variance it's relative to is, people error or item error. So at the time, I'm listening to this story, and I'm like, wait, I just learned this thing called multi-level modeling, or I'm trying to anyway, it's really hard, but I think this could be a multi-level model. I think you could have items nested in people, and multi-level will just fix it, it'll be great. So we start working on this paper with this idea, and I go to a conference, and I realize that someone else has this idea already, and they're presenting about it in front of me. And they correctly point out that it is not items nested in subjects. Because in the same way that you can think of items as nested in subjects, you could also think of subjects as nested in items. That's the F2 version. So anytime you're not sure which way your nesting goes, it's crossed, not nested. That's the answer. If it can go either way, by definition, it can't be nested. So I was sitting there listening to this, and I was like, oh crap, they're right. And so went back and tried to fix the paper, fix the analysis, and learned something new along the way. So this is the end result of the story. We did end up publishing a paper on some data that didn't work for the reason the study was conducted, but now it's the token example in a methods article. And it's been decently cited too, so this is from 2007. So there's the background.
Cool.
Now, connections to this, where we are headed, for those of you from measurement model land, is quite adjacent to explanatory item response models. That is the same concept. So just keep that in the back of your head as we walk through this, like building towards that as an essential endpoint. Question?
Before you move on,
Yeah.
That sense to explanatory IRT, can you clarify what adjacent?
I'm sorry, can you say that again? I can't hear you over the airplane.
Yes, you said this is adjacent to explanatory IRT.
Yes, adjacent.
Can you specify why you use that? Adjacent, is
Yep.
it the same thing or what makes it different?
It is an IRT model if you swap out logits for normal distribution because it's a plausibly continuous residual. That's why. So I'm predicting response time, and I'm pretending that that's continuous. IRT models are typically for categorical outcomes, so they would have link functions and different distributions. But if you agree that general models are a subset of generalized, then I can call this an explanatory item response model, just without the link functions being needed. Yeah, that's what I mean.
We've encountered this problem before.
You have encountered it before?
I had the misconception of items nested in subjects. Well, I was lucky to be working with Vladimir, who said that is not right. So, yeah.
Well, it's tricky. So this is a whole thing. I've given talks on it. I'm sort of like giving the talk without giving you the slides. So this is just me whiffing, speaking contemporaneously, excuse me, is that the right nicer word to say that?
Sure.
Oh, I can break out the GRE words every now and again if I need to. That sounds better than I'm just making shit up, because I'm not. So I have a paper with someone who was studying autobiographical memories and characteristics of those memories. He's a cognitive psychologist. And the task that he gave subjects was, I want you to write a paragraph about 10 different events in your life that you felt this way. And then he analyzed what they wrote and picked out, features of that to predict differences in responses. In that situation, in which an item is a memory, do you think items and subjects are crossed? This is where it gets tricky. So like if the 10 were write about, your parents, write about your pet, write about, high school, write about this, then you're closer to something that's more like a standardized item. But the instruction was just 10 things.
Non-standard.
Yeah, the non-standard, I would argue, makes it sort of nested instead of crossed, because each person has their own unique set of memories as their own unique set of items.
Mm-hmm.
So in that case, I wouldn't say they're crossed. Another example is I have a paper looking at essentially how people's speech changes as they're doing some other kind of motor task. So you can have them walk around in a circle and measure how fast they go or how aligned they stay to some target. In this one, they had a mouse that was having to track a ball, like going around the circle while they were talking. Well, these are older adults, so mousing is sometimes trickier for folks. And so in that case, the items were individual like trials of like a sentence they said or their path around this thing. And I treated those as nested as well because it's like each person's sentence is their own unique item. So I would say in the case where everybody responds to the exact same items, it's clearly crossed. In the case where it's your own unique whatever, it's clearly nested. In between, there's kind of some gray areas. So if, for instance, if you build items using some kind of test blueprint, like you have a set of features that you're going to vary algorithmically to induce differences in item difficulty or severity. Well, if you build an item with the same blueprint, even though it doesn't turn out to be exactly the same item, like, is that crossed enough? Like, is it standardized enough? Depends on how good you are at predicting difficulty. So there's a little bit of gray area in there. I think these designs are really, really interesting because they get super complicated super quick. This one is straightforward because each person responded to each item only once. So there's no potential for random interactions, and there's only limited potential for random slopes as well. So there's the longer version of the story. So heading towards connections into measurement models, because in measurement models, items are treated as fixed effects instead. This is what happens if we treat them as random, which is this class, not the other ones. So questions or thoughts on that? All right, so response time in milliseconds is what we're here for. 1,482 total observations. That is fewer than one would expect based on this number of items and this number of subjects. However, after we remove inaccurate responses, this is how many we have left. So in these designs, if you don't get the answer right, they don't count your response time. They treat it as missing data. What do we think about that?
Bad.
Why?
Great question. I asked Larry this. Because if you get the answer wrong, we don't know what process you used to solve it incorrectly. And so we don't want to measure response time for a different process than what you ostensibly used to decide correctly that it was a word or a non-word. That's the answer.
And they are not interested in the accuracy for the subjects.
Nope, they're not interested. Accuracy is just sort of like, oh, everybody was 90% or better, it's fine. What do we think about this?
I'm thinking there might be difference in response time based on if people actually get it correct.
Yeah, I think there's differences in speed, and I think there's differences in how much people pay attention. I think accuracy is probably relevant in most cases.
And I don't think people are always thinking the same path to get something right.
Exactly. And I would argue that somebody who, like if it's a task that's difficult, people who are good are going to take longer for a difficult task than they do for the easier tasks. But people who approach the difficult task and are not good at this task may get it wrong, and their response time's gone. So now it looks like they're actually faster on average when you take the aggregate of the trials that are left that they didn't knock themselves out of contention with. So that to me sounds like the definition of not missing at random, like missing for reasons.
Mm-hmm.
And I would probably want to do something different in that case. Question?
Lisa, to me, in my mind, for instance, we could try to fit something like a hardware model because we could flag those incorrect responses as zeros, for instance.
Mm-hmm.
But in this case, zero would be something good because it means that the response was almost at the same time that the stimulus was shown. What could we do in this case?
I'm so glad you asked, because I was honestly going to explain that next. Yeah, so it was like I planted it.
I think you planted that
Yeah, I didn't
question.
intend to, but well, again, they've been sitting in the back of the room for like 4 years now. They should know the stories and know where I'm headed and all that kind of stuff. The rest of you don't have to have perfect memory of what I said last week, but my grad students probably do at this point. So yes, not a hurdle. So this is a generalized modeling concept. They are known as two-part models when the amount part is continuous like response time. A hurdle model is what it's called when the amount part is a count distribution. But the key idea is that what the best way to do this would be to turn it into a multivariate analysis, where you first predict the probability of getting the answer right as one outcome, and then if you're right, how long it took you to be right as a second outcome. So I call that if and how much as a concept, because it's like the first one is like a gateway that you have to cross to get to the second. And so then in the analysis, the binary outcome would adjust for mean differences as a function of accuracy, and the continuous outcome then would scale those who are in the distribution that have a response time. That's what I would do instead. So two-part is what that's called. For something like response time that's plausibly continuous, it is called a hurdle model for count distributions, where they have a non-zero part for the count.
So the subjects does those include like the people with special needs?
Not in this sample. This is just a bunch of undergrads and intro psych who had to take this experiment for course credit. But no, that is how psychologists roll.
Yeah.
Like, I was that subject. I was the undergrad helping to run said subjects. I became a faculty member who had undergrads running said subjects. Like, it's just, that's how we do it in psychology.
So your population is just psychology students.
19-year-old psychology undergrads who are like, usually white, usually this, usually like from, the University of Kansas where this story takes place, or the University of Nebraska, or the University of Iowa. Kind of very similar across the Midwestern rectangular states. But anywho, yes, that is how I would have done it. But this is not the story right now. We're just going to go with response time. In these designs, people get very few trials wrong, and it's usually some kind of inattention marker. These trials are not meant to be difficult. This is supposed to be like an instinctual response. So we're not going to worry about that for this purposes, but just know that in life, accuracy and response time should be dealt with in a principled manner. Okay, you want to see some examples? Some code? Some concepts? Why not? All right, here. So loading packages, as usual, all the things.
What are all those warnings that you skipped over?
Which ones?
I just saw a warning.
Oh, yeah. Well, these aren't supposed to really be warnings. This is just saying that whatever I ran this on had a different version of R than whoever made the package. And sometimes that's a warning because things break, and sometimes that's just an advisory.
Only because I thought that maybe you in particular said there's a warning about using this. Not the message given while loading. You may encounter this.
Yeah, and you're making a great argument for why Markdown is maybe not as useful, because you can't tell what are comments and what's output. So this, for instance, these are my comments. This is an error message from R. I guess it's the two hashtags that make it different. Oh, well, that's, super obvious.
So don't use two hashtags with your comments and be done.
Say, can I change the colors in here? Do you guys know? Could I make this something other than burnt orange? No? I can make it green, but like this one and this one, could I make it different colors?
In the output?
Yeah, so like in the Markdown document, that the comments are differentiable from the error messages.
As far as I know, you can't.
Okay,
But
I was gonna play with it more.
templates for Markdown. So if you can specify that specific type of text, you can define a specific font, style, and color.
So it's like a CSS cascading
Exactly.
style sheet.
Yes.
Okay, gotcha. Good. I will play with that because this is confusing. But for now, it's burnt orange and two hashtags instead.
Okay, sorry for.
No, it's fine. Question.
The tone can be turned off too in the R Markdown,
Oh, okay.
Not showing in your output.
Yeah, I wanted to have the output for most of it, I just didn't want like the stuff that we would normally not pay attention to, so to speak, but this sort of dumps everything in one file. So point of the story, I've got some more learning to do, it sounds like, if I want to get better at Markdown. I'm just not sure I want to. Just not sure about that. We'll have to see.
We have time.
Yeah. Well, you know, sometimes you just have to decide you're not going to be good at something and just let it go. Like, I'm just not going to be good at cooking.
That's
I'm
what
not. I'm
restaurants
not
are
good
for.
at keeping plants alive. There's things I'm just not good at, and I'm okay with it. Yeah. I'm not good at speaking German. People laugh at me when I say Entschuldigung. And I'm not sure why that's funny, but apparently it's a very bad pronunciation. All right, so our data set is long. So that means it is one row per subject per item response. So first off, that would be very different than how these data would typically be stored by psychologists. Usually they have a file where it's one row per person and all the variables would be across. So that would be the first step, is to make it into this long shape right here. I did a bunch of descriptive stuff, sort of like for let them know about the data and the sources of variation. Let me get to the R section here. So I have only 3 variables in the story. I have response time. I have whether the word is part of high frequency or low frequency words, and then whether it's part of a large or small semantic set size. So essentially zeros and ones for these things. Question?
Just for learning's sake.
Mhm.
So is that how you would actually pull any particular column out of a data set into a new data set if you want to work with it separately?
That's not
with the quotes around the RT and so forth.
So this little piece here would be used anytime you want to collect those variables and do something.
Okay.
But this function, what it's doing is kicking out incomplete cases with respect to these variables. So this is a subsetting
So
function.
it's just subsetted from the 5Bs, got it.
Yeah, and because I didn't need to save the original
right.
that had any missing rows.
But,
So
but if you wanted to do that, that's part of your step, got it.
yeah, and I didn't need to in this case, but had I had missing response times for inaccurate trials, that'd be one thing. And if you don't know what a predictor is for a given item, you can't use that item. So these ones would be a bigger issue if they were missing, because that would knock an entire item out of the analysis.
All right, thank you.
So on average, it takes people about 632 milliseconds to decide if something is a word or not. So just for an hour or so. And this is variance in milliseconds. 21,340 is in the total overall data set. So we'll have that number to compare against in looking at how to think about the means across subjects and items. Because I have complete data, I was able to use a function that I found, ABE, to make a unit mean. So the make unit means, or whatever function I've been using this semester, I think does a better job, but this is a quick and dirty version that will work in this case. So I created a subject level data set using unique here, and in it I wanted to see what average response times were like across subjects, as well as how many subjects contributed to each item. So in that little data set here, subject mean RT is 631 on average, but you can see there's quite a bit of variability. So these are variance in the person means across items. So some people only took 501 milliseconds to respond on average, some people took up to 783. So this tells me just descriptively that I expect subjects to matter as a random factor. There are mean differences across subjects that a subject random intercept is going to represent as a source of unexplained variability. And what kind of predictors do you think would explain this? Subject things. Yes, why are some people faster than others? It has to be people things. And we have 38 observations per item. Did the same thing for items in this case. So I have the number of items per condition, almost perfectly balanced. I don't know why there's only 9 in this one, but for certain combinations of linguistic properties, like those words don't exist, and they're very difficult to find. I do know that. Likewise, items. So each item has differences in how people respond to it on average. So some items are super easy to respond to quickly, 570 or 567. Some items take longer, 833. and then number of items we have here. Okay, so we know then there are differences in how fast items are responded to. What's going to predict that?
Items.
Item things. Why are some items easier than others? Maybe they're shorter words. Maybe they're less common words. I don't know. I don't know what makes words different. That's not my lane.
Different languages.
Yeah, I should have recruited a guest speaker for today to help me with this, but at the end of the day, I just need to know X and Y. Like, I don't really need to understand the theory.
Even the case whenever you analyze data.
Nah, well, I need to make sure I'm not doing something ridiculous. But other than that, right?
Mhm.
As long as they know what X is. To me, X is a binary variable. That's what I got. So I have my Stata models, and that's all I get. So after this point, Stata craps out, unfortunately. That's a technical term. Experience convergence difficulties, and therefore subsequent results were not reported. Translation, Stata crapped out. Sorry, can't.
Kick the computer.
Yeah, that doesn't help. So starting at the lowest level, empty model. So my subscript here in terms of notation, RT for response time, TIS, trial item subject. Now in this case, T is not strictly necessary, but I left it there because I wanted to allow a spot for any trial level predictors. So I say it's not strictly necessary because once you know which item and which subject a response is from, that's all you need to know. You know what trial it had to have been. However, do you think that people get faster at this as they go on? As you get practice at the task? Or maybe after a
Or you
while
get
they start to
fatigued.
lose their will to live and they don't want to do it anymore and they get slower and careless?
Mm-hmm.
Both of those things could be true at the same time. So in these designs, items are always randomly presented in terms of their order. So I could control for whether a trial was first or second or third as a predictor. And that would be a level 1 trial specific thing because it pertains to the unique order that subject was given for that item. So because there is the potential for trial level information to factor in here, I left the T. So ETIS. So this model is not a multi-level model. What would I call it if you only have one variance component at level 1 and it's E?
The general linear model.
That's what it is. This is an empty single level regression model. I'm starting there. Because theoretically what should happen is this fixed intercept should be the mean
Mm-hmm.
of response time across all the columns,
Mm-hmm.
and the variance of these E's should be the variance of response time.
Mhm.
So like just locking in, we're starting to, by representing the salient moments of an outcome to start with, and then we start partitioning this E into different reasons why it's there. So I had to fit this in GLS rather than LM so that I could make sure that it was, that I got the -2 log likelihood out of it to use as a point of comparison. Otherwise, it would be the same thing as LM. Yes?
Sorry, it's about the data structure. You
Mhm.
said that every subject had all the items, but some of the responses were not recorded because they were wrong, right?
That's correct.
But we know that at the beginning of this thing, every subject had, let's say, the 30 items that were supposed to be analyzed later.
Yes, every subject was administered every item. Any item responses that were incorrect were deleted.
Okay, so I have a quick question about it. In terms of missing data, I know that you mentioned that, but we have incomplete data in two senses, right?
Mhm.
We have incomplete responses, but we also have incomplete subjects for some items,
Mhm.
right? If that's the case, we know that we are using maximum likelihood, so we can work with this assumption of MIR. But if we would like to try to impute this data, how could we think about multiple imputation in this context, given that we have like two different perspectives, missing people or missing items? Have you heard about something like that kind of multiple imputation?
So let me repeat the question for the recording. Missing data here is like if you picture just a giant matrix of subjects by items, there's going to be some holes in the matrix because of incorrect responses. Under the assumption of missing at random, if you're using regular flavor maximum likelihood or the residual version, which is what I have here, The idea is that like the shape of the likelihood function would be the same even if those extra holes were filled in. And asymptotically, if you put the same information into your multiple imputation model as what goes into your analysis model, you should end up at the same place in terms of the answers that you get back. So, but to answer your question, what that would entail, your imputation model would need to have random effects of subjects and items. It would need to have fixed effects of the two predictors that we care about, the two binary variables. It would need to potentially anticipate interactions and random slopes and other things. So I don't see that there would be a benefit to multiple imputation in this case because the same information that has to go into the analysis model would go into that.
Okay, yes, yeah, that makes sense. Okay, thank you.
But if you just ran like mice or something on a single level regression model to fill in the holes, that's bad. Don't do that. And don't ever let SPSS fill in the holes for you directly with just one number. Don't do that either. It's still a thing. They call it single mean imputation.
Yes.
Very bad. Okay, so I get my -2 log likelihood value for the sake of comparison. That's why I did this in GLS. And lo and behold, my mean of 632 comes back, and this routine doesn't spit out variance, of course. I have to go find where it's stored and ask for it. But the variance number that I get back is the same thing as what I got from the data set. So good. That's always reassuring. Yeah, I start with empty models to make sure I'm not crazy, honestly, to make sure that things are working the way they're supposed to. Empty model 2 level for trials nested within subjects. So note the terminology here. I'm not going to read my words to you, by the way, but this is like the full story of all the things that you would say about that. This is still an empty model because there's no predictors. We added a random intercept. Is that for subjects or items? Without even looking at my words above, how can you tell? Hide my words.
I think it's subject,
Subjects, you're right. Why?
because of the S.
Because of the S, exactly. So this is why notation matters, folks. The S turned on here indicates that this is a random effect of subjects.
Why not we start with the item first?
Why not start with items first? I could have. I don't think there's a right way to do this. But from the perspective of psychology, items are exchangeable, whatever. We care about the people. So I would start with the people because that's like where I'm from. But if you want to start with items first, sure. I don't think you actually have to do this sequentially because if you use Renova, it fits nested models that take out each of them. So you don't have to build sequentially, but I wanted to do that for pedagogical purposes to show what happens to the relative variances in that. So you can see what happens. So I have level 1, I have level 2. And I don't usually get this technical in handouts, but I wanted to be complete. What's the difference between this symbol right here and this symbol right here? That and that. Actually, this should not be a capital S, I think. There. What makes this different than this?
The tau square,
This one?
yes.
What is it?
Tau square.
It's tau squared, but what is it?
That's the random intercept.
That's the random intercept variance across subjects. So what is this?
Charge is the actual deviation from the fixed.
Yeah, this is the random intercept specifically for subject S. This is their value for how far off their subject mean is from now the mean and the subject means. So this is an easy thing to screw up when you're writing about these models. Are you talking about this as a random intercept in a model, or its variance across subjects as what's being estimated? Tricky, but it's important to be clear. So this is why I have this here to show that this is a random variable that has this distribution, mean 0, estimated variance. This is the same deal. Okay, so what happened? We should guess. So we add that per usual here. And it looks like, hey, subjects differ from each other. As well they should. We knew that already from looking at the subject means.
We can split apart.
Yeah, so the intercept is a little different. It's now the mean of the means, so it's a weighted mean, but very close since most of the data is balanced. And how would I convey to regular people how much subject mean differences there are? Is it like most of it, a little of it, some of it?
About a quarter.
About a quarter? What did you do in your head to answer that question?
Well, you originally started with like 21,000, and that's 5,000-ish, and 5 out of 20,000 is about a quarter.
Yeah, so you're computing intra-class correlations in your head, is what you're doing there. So yes, 24% to be specific.
Oh, not too bad of a guess.
Yep, so the original variance that we used to have, 21,340, is close to but not equal to the sum of those two variances. It's not going to match. Only in very specific circumstances with specific versions of the estimator will they match exactly, but there should be ballpark. Yeah. So of all the differences in response time, 24% of that has to do with some subjects being faster at this task than others, on average. Do you think that's significant? Nah. I think it is.
It's not 80%.
Yeah, it's not 80%, but it's something. All right, so then I wanted to show them how to store and access these numbers to do computations. You've seen this before.
Yep.
So I'm accessing a varchar function that spits out this table into a matrix I can then work with. So I'm computing these things for them themselves. And Renova says, yes, test statistic of 280, decidedly. So this is the significance test that goes with that intra-class correlation. Is 24% greater than 0? Decidedly so. And then I did the math for them because they hadn't seen likelihood ratio tests at this point either. That's the fun of teaching a workshop, is that you have to stop and explain every single thing because you never know where someone hasn't seen that before.
Or they don't recall it.
Yeah, or
It's
they
been 20
functionally
years.
have not seen it before,
Yeah.
that kind of thing. Yep. All right, got to fix my own too. There we go. So empty model 3 then.
Woo.
Yeah, apparently I decided to go with capital letters here. There was a reason for that. I'm not privy to it today. That's okay. Now I'm picking up another random effect. So do you think its variance should come out of E, or do you think its variance should come out of the subject variance?
You know, I'm there.
You think E?
I'm there for this time.
Yeah, this is for item. My question is, like, variance can't be created nor destroyed, right? Like, it's like all in one pile.
Actually, I think it's going to come from both.
Well, there's a question. So this is going to basically take some of the variance out of these two. Is it going to take it from this one or this one is the question. Well, we got to vote for both. We got to vote for E.
If they were orthogonal, then I would say only E. But I think there's some.
Because of the
interaction.
missing day there may be a little bit of slippage. But yes, it should theoretically just be E.
Yes.
But that's not what's going to happen. So E has indeed been partitioned further into this new item random intercept. It looks like it's like numerically smaller, but it's there. Intraclass correlations. So we went from 0.24 to 0.236 for the proportion due to subjects. There's your wiggle, but it should stay about the same theoretically. So we can do an intraclass correlation that describes how related item responses to the same item are. That is 0.11. So you can think of that as the correlation of responses within an item, or you can think of it as the proportion of variance in response time that reflects item mean differences. Then 24% or so is due to subject mean differences, and the rest is due to trial level item by subject interaction. So these kinds of intraclass correlations you will see in the world of generalizability theory as indices of reliability of different kinds. The big difference, though, would be in estimation. So in this case, we have missing data for some of the responses, right? If I tried to fit this same model using random effects ANOVA, and ordinary least squares estimation, what's going to happen? What happens to my holes in my matrix? Am I allowed to have holes in OLS?
No,
I'm not.
you just lost a lot of data.
Anybody who missed anything is gone. And any item that not everybody answered is gone. So you may not even have any data left at that point. Yeah. So that is why the mixed models world is much, much more helpful when you have designs with random effects than standard stuff because of the missing data and unbalance. Not everybody has to see all the items too in mixed effects land. It doesn't have to be perfectly crossed. So I would highly encourage folks who are thinking about differences across different sampling dimensions in the context of reliability to go with this route as opposed to anything else that might have been an older method, subject to limitations of missing data. So in Larry's analysis, I only have 2 predictors. I have low and high on 2 different item things. Best case scenario. How much variance in response time am I explaining? Best case scenario. 11%. Because 11% is why some items differ from each other. And whether that item is a low or high, whatever, can explain why items differ from each other. Can whether that item is a low or high, whatever, explain why people differ from each other? It cannot. So logically speaking, without subject predictors and without trial level predictors, 11% is the best we can do. So for these kinds of designs where one dimension is really what you're focusing on, I probably wouldn't do a total R square. Because it's going to look sad. Because you only could have got 11% at best case scenario. And we're not even going to get that far. All right, so then more fun with math. This is a longer, less efficient code because I was still learning how to do this stuff at that point, so forgive me. But, you know, here's how I got those things. And Renova says both of these things are needed. So Dan, to your point, if you wanted to go straight from an empty model with no random effects to this one, that's fine because each of these tests is going to tell you what would happen if the other one wasn't there. So that you can save a step that way. Computed confidence intervals using the fixed intercept for the middle and then the corresponding random effect variance for the standard deviation. So you can see that subjects differ from each other on average a little more than items do, which is consistent with the 11% versus 24%. And that's where I found all those numbers. Last data model, because we're adding an interaction term. And that's the last one I got for that. All right, so the thing that Larry cares about, whether low versus high on my 2 item predictors matters. And note I am using composite notation still, because 2-level notation for multiple sets of level 2s gets real ugly real quick. So I have, this is O10, O20, and O30, because I is the middle number. So this is the first predictor, second predictor, and then their interaction is the third predictor. So let's see what happens. Yeah, we can do a little practice with interaction terms. So these are all coded such that the low group is 0 and the high group is 1. So for an item that's low on both characteristics, their average response time is 615 milliseconds. What about the effective frequency? What if your item is of high frequency instead of low? Yeah, response times are slower or higher, however you want to talk about it, significantly. So there's a 70 millisecond difference. You're slower if the item is more frequent. However, is that the end of the sentence? The effective frequency is 70 milliseconds, period? Nope, what am I missing?
Controlling for size.
Not just controlling for,
Assuming that it's 0.
conditional on size 0. So this is only the slope of frequency when the interaction term drops out. But look what's happening. The interaction term is knocking it out.
Interesting.
Yeah. So there is an effective frequency for smaller sized words, meaning network size, essentially, how related it is to other things. But then in higher frequency words, that effect is gone away and actually goes a little bit the opposite direction. The other way I can do this, let's see, there is really no effective size for low frequency words, but then that switches to become a negative effect in high frequency words. So I made a bar chart, I think. Let me see if I can just find it. It's in here somewhere. Oh, no, I didn't. I couldn't figure out bar charts, so I did a line plot. Sue me. I have a bar chart somewhere in Excel, I think. But yeah, essentially the story is there's no effective frequency for large words. There is an effect for small words. I have no idea if that means anything, but we'll just go with it. So then I walked them through how to get predicted values for each condition. Walked through that. So if predicted RT is a function of these as our fixed effects, then I can write contest 1D statements to get predicted values for each of the combinations by turning on and off the zeros and ones. So I've made you do this like 8,000 times.
Yeah, I couldn't use it on mine. I had to make my own.
Well,
But that's okay.
it's not
I
perfect
learned.
on the first try.
I learned.
Likewise, we can also get predicted frequency slopes for either size and predicted size slopes for either frequency. So I walked them through all of that because I didn't know if they knew that yet either. You never know. Question?
How did you determine the interaction term with the frequency and size? Like, how do you determine like whether or not you need an interaction?
How do I know if I need the interaction? This p-value? It's a fixed effect. So it's less than 0.05, I'm going to call it good. So let's say that I shove these data into an F1 ANOVA and then into an F2 ANOVA as described at the beginning of class. Which result do you think is going to be closer to this one? Aggregating over items to talk about subjects in a repeated measures ANOVA, or aggregating over subjects to talk about items in a between items ANOVA? Which is going to match this closer? Voting for 2?
I'll trust Vladimir on this one.
They're all voting for 2 now. It is, because essentially what's happening is that these item effects are being evaluated as predictors of random item variance. The F2 ANOVA has random item variance as its error term, collapsing over subjects. So the fact that we only care about item things means the F2 would be the closer analysis. But what if we also cared about subject things? Well, then either one of them is going to be wrong. So I think that even if you don't have subject predictors or item predictors, you would want to account for random differences anyway. Yeah, 123, we're doing okay. So up to this point, you could sort of make an analogy that this is like an F2 ANOVA, but just fancier. And you would come up with the same components. How much variance did we account for? We got about 30% of the 11%.
Ooh.
So that's like 0.03 altogether. It is what it is. It's only 2 variables. We had a slightly negative amount of subject variance, R squared, and near 0 for trials. Surprising or unsurprising? My item predictors explain no subject variance. Is that surprising or unsurprising?
Unsurprising.
Unsurprising, yeah. And it explained no trial level variance either. Okay.
That's actually good, isn't it?
I wouldn't expect it to move. Yeah, because it's not a trial level thing. It's an item level thing. Yep. This test I did is to test whether or not we still have random item variance. So in chapter 12 of my book, I have an extended discussion on this, but the fact that this is still significant indicates there are differences among items of the same kind. Said differently, we've explained 30% of the 11%. Is that 30% good enough? This says no. That 70% that remains is significant. So this tells me that Larry didn't do as good a job as he thinks he did in controlling his items, right? There's still differences among the 10 items ostensibly of the same kind. And I remember when I talked to him about it, he's like, well, of course there are. We didn't put in all the other things we controlled for. We controlled for length and this and this and this. And I'm like, why aren't they in the model? And the answer is because you can't shove those things into a repeated measures ANOVA very easily. That's why they're not in the model, but they could be. So all of the careful balancing and selecting and controlling that Larry did in building his stimulus list isn't being taken advantage of. That's sad. That's a missed opportunity. Had he put those things in, he would have more power to detect his item effects because there'd be less residual item variance left over. Same principle as you're learning in design. It's the same idea. So I think the benefit of this approach is not just dealing with missing data, it's not just unbalanced data, it's the capacity to build in extra things that don't fit neatly into boxed ANOVA length. One of those extra things could be the idea of a random slope. So in my ugly plot here, we'll go back to this, it looks like there is an effective frequency in small words. Do you think that that effective frequency is the same for everybody? Or maybe some people get a bigger boost from frequency. Maybe those are the people that do the crossword every day. Could be. How could I implement that idea that some people have a bigger effect of item frequency than others? The effect of an item predictor varies over people. What's that? Close. I mean, yeah, technically yes, but not the right word I want. Like each subject needs their own slope for frequency. Hey, random slope, yeah. You're not used to thinking about subjects as having random slopes, but in this case they can because subjects is level 2 relative to trials. So essentially because this is an item characteristic at level 2, it can have a random slope over the other level 2 dimension of subjects. So the manipulations that people are building into these experimental designs might not have the same impact for all the subjects, and the extent to which that impact is different is an empirical question, testable via random slopes. That is nowhere in ANOVA land. So we'll see. Do you think that subjects need their own effective frequency? Well, I'm going to put it right here. So frequency with an I is attached to a random slope with an S. You can't have a random dimension over itself. But item predictors can be random over subjects. Subject predictors can be random over items. And note where it goes in my little notation here. Because I already have a subject random intercept, the subject random slope should get a covariance with it. However, subject random effects are not correlated with the item intercept. That's like separate. Does that make sense? Yeah, not all random effects are correlated with each other, only the ones that pertain to the same unit at the same level. So because I've added a variance and a covariance, that's the degrees of freedom 2 change relative to the previous model. So frequency is going to go in the parenthesis with the subject ID. That's an easy thing to screw up, so make sure if those of you doing cross models, we got to watch that. Let's see. I have a variance here. It's not 0. It's not yelling about convergence code. Okay.
It's like 1% maybe.
It's a little, yeah, it's there, but it's kind of small. Yeah, so if we go down here, look at Mr. Likelihood Ratio test. Oh.
Oh, I was right.
Yeah. 4.87. So this
That's
is not,
close.
this is close.
Now, a question for you.
Yeah.
Because you mentioned earlier there were two values, maybe this is, I'm thinking of the wrong test, that typically like 3.8 whatever or something, and but you might have to go to 5 point something or
Yep.
another.
That's where I was going to go next.
Oh,
I planted you too. I have more power than I thought. But yeah. So this is where you might want to go to the trouble to do the mixture chi-square test. The difference is the critical value if you ignore this problem is 5.99. The critical value if you attend to it is 5.14. So this would still not make that standard, but it's close enough that you might want to do it the righter way.
Mhm.
Did I do that in here? I feel like I might have. I did. Oh, look,
Of course you did.
I did. Previous me knew future me would make this point, so there we go. Yep, I computed it myself. So what I did essentially is compute the difference in lines 2 log likelihood, and then get a p-value for degrees of freedom 1, a p-value for degrees of freedom 2, and then add them together equally weighted to create the mixture p-value. In more complex designs with more parameters added that have a boundary problem, this simplistic approach will not work. But for this little situation, it should be fine. And like 3 people on Earth know and care about this difference anyway, and I'm not one of them.
And it would be my reviewer number 3.
Yeah, reviewer 3 possibly will care. In terms of just descriptively, the individual subject slopes for frequency would range from about 32 to 107.
That's pretty big.
It seems kind of big, but it's noisy.
No, that's milliseconds.
Yeah,
though.
this is milliseconds.
That's like 0.1
So
second.
can you, these are literally really tiny differences in milliseconds. Here's some math showing how I got those numbers. How about the other predictor for size? We can have a similar process, test that out. Even smaller variance in that case, and decidedly non-significant.
Did you try them at the same time?
You could try them at the same time.
Well, I'm asking if you did. I don't.
No,
know.
I didn't go there.
But
I
you
decided
could.
that was like the end of the handout.
It probably would.
So,
It probably
there's-
would have been like even. Do you think that the amount of variance individually would still be about the same, even though you combined it, or do you think that they would probably be a little bit smaller for your variance?
I think if both random slopes were in the model at the same time, like theoretically that shouldn't be a problem because the design tried to perfectly balance between frequency and size.
Mhm.
But yeah, if this were a regular set of measured variables, then I think they might steal from each other in a way that would be problematic.
Okay.
However, let me go back to my ugly picture. Here it is.
Not that ugly.
It's sad, okay? I know better. And I'm not going to throw stones. Like, if this is what's in your presentation and you know how to talk about it correctly, I will live with that.
Mm-hmm.
I would much rather have you explain your results in meaningful ways than make the prettiest picture on Earth and not be able to talk about it.
Mm-hmm.
That's what I'm going for. But, so the story here is that the frequency effect really only happens in small samples, or small whatevers, right? Sizes. Did my random slopes actually test this?
What did you do that?
So this is an interaction pattern
Mhm.
where there's an effect only in one condition of another variable. I just added random slopes as main effects. So did I test individual differences, say, in this blue line? I didn't. I tested it in sort of like the average of blue and red because I didn't control
Well,
for the other
blue
dimension.
would be your that's your center line almost, isn't it?
Mhm. Yeah, I tested a main effect random slope, not this blue one. So I also could potentially have in here a random interaction term. The extent to which frequency affects size differently could vary across subjects. That's not going to work. I will tell you that right now, because that would require 2 main effect random slopes and a random interaction term. But what those would allow is heterogeneity variance across the 4 cells of my design, it might actually be cleaner to switch to a multivariate version of this model, where I essentially would have 4 different random intercepts, one for each combination, and that would get me to something that would be largely equivalent. So that's probably where I'd go next. Differences within cross conditions can be operationalized as multiple random intercepts when those combinations are categorical, and that will probably work better.
Cool.
Yeah. And that's it. So then here's some words.
Awesome.
Yeah, lots of words. Well, the words matter.
They do.
Yeah, gotta get the words right.
Yeah.
Or at least the equations, one or the other.
Equations.
I put equations and words in my papers, so you can skip whichever part doesn't make sense to you.
Sorry.
Well, there's like a rite of passage when you're reading published work. Like when you're young and naive, you read the intro and the discussion and you skip the middle, and then you stop trusting people at some point and you go straight to the methods and results and you don't even read what they thought they found because you don't believe them. So, anywho, questions, things you want to ask about before you dive headlong into your projects. I know we're not meeting on Thursday, and that next week we don't have classes, but you can still be emailing me questions, okay? I'll still be working and trying not to freak out about how much packing I have not done yet.
Movers.
Yeah. So let me know if you need help, okay? Question or comment, Vladimir?
Yes, just a quick question, Lisa, now that you are here.
Where have I been?
Contractually obligated. No,
Then
sorry.
I want to ask questions, but you are not available. So, Lisa, to me, I work with similar data. Well, we worked with something similar like 2 years ago for a Jonathan's project.
Mhm.
And I think that I asked you this because we were working with pigeons. So we had different pigeons and different trials.
Oh, I remember
So
the pigeons. Yeah.
We were trying to predict the pigeon's probability of a correct answer for a specific trial. And I remember that I read chapter 12 in your book, but it wasn't clear to me. I didn't have experience. But that was me because I didn't have experience with this. But back in that year, we only had like 2 or 3 pigeons. So those pigeons had like hundreds of trials.
Yes.
Thing
You're
is,
mean to the pigeons.
yes.
Poor
So
pigeons.
if we would like to do something like this, let's say we know that we have a cross-classified data.
Yes.
We have pigeons and we have trials. However, we only have 3 pigeons. Could we add those pigeons' IDs as fixed effects in the model? But then we were also interested in the potential, in potential pigeon differences in some things.
Can't do both. Either you put in your 3 dummy codes for which pigeon is which, and you talk
Actually,
about,
two, but,
yeah, well, however many you had, then you talk about pigeon A and pigeon B, but you can't predict differences across pigeons if there's only 3.
question.
Oh,
Well, I have a question related to yours though. Wouldn't you have 2 dummy codes if there were 3 pigeons?
Yes, if there's only 3, there would only be 2.
Okay, sorry. I just want to make sure I wasn't. Sorry, Vladimir.
no, that's okay, thank you. In that case, Lisa, could we add some kind of interaction at least?
Yes, so if you took the pigeon dummy codes and you interacted them with things, then you would have fixed versions of how pigeons differ in their response to whatever. But you could only make an inference about pigeon A did this, pigeon B did this. You couldn't talk about
Yes.
pigeons that have gray hair are going to do this in the future, as opposed to pigeons that have white hair or whatever makes the pigeons different.
Got it. Okay. And that thing can be generalized to any other context. Let's say that we have here like 100 subjects, but just 3 items or 4 items.
Yeah, fixed effects, that stuff.
Given the lack of power, we could use a fixed effects approach and then add interactions to explore potential item differences.
Yes.
In the segment. Okay, got it.
Yes, and so to try and tie this all back together again, I told you at the beginning, yes, I got 5 minutes. Okay.
You got plenty of
I got
time.
5 minutes. I can tie it together in 5 minutes, I promise.
Ooh.
Explanatory IRT models is where I started with this, right?
Mhm.
I would argue that's what this is. The only catch is that IRT typically refers to categorical outcomes, whereas this is continuous. However, what we have is random item differences. Now, how does this compare to, say, a confirmatory factor analysis? In those models, we let each item have its own fixed effect. Item parameters in measurement models are intercepts or thresholds, or difficulties, take your pick, whatever you're in. And we say item 1 has this one, item 2 has this one, item 3 has this one. In the same way that I just said, pigeon A has this and pigeon B has this. It's the same. So in measurement models in which items are treated as fixed effects, meaning each item gets its own difficulty or intercept, it gets its own discrimination or slope, then you're not trying to generalize across items. Why is this item more difficult? You're just saying item 12 is hard, I don't know. But in explanatory models, rather than just saying, what did item 12 do, what did item 13 do, you're estimating a variance in item difficulty. Technically, this is easiness because it's an additive model that allows you to then put in item predictors like frequency and size, or gray hair versus white hair for your pigeons, or whatever other random characteristics you want to control for. The only catch, though, is in this framework, in standard multi-level software, there's no place to stick discrimination. This is a Roche model. There are no different slopes by item. There could be, though, in life. Like, that's a thing that people have done. And it's possible in M+. I'm sure you can roll your own whatever and stand to make this happen. You probably have even seen code for this. Ahmed's doing this in his dissertation, for instance, I know. So you can put a linear predictor on discrimination in these models, too. Why are some items more predictive or more related to the trait? Maybe items that have higher frequency are also more discriminating. Like, that's a thing you can do. So the intersection of multi-level and measurement models is actually like right on each other. Like, they're not separate. A random effect is a latent variable, and theta is a random intercept in a Roche model. Once you understand that and you figure out slopes on and off based on software, you're home free. Cool stuff. And since this is a measurement program, damn it, I'm going to make that connection.
Talk about measurement.
That measurement and statistics are on this page, and I want you to tell me which one I'm teaching right now. There.
Slam dunk.
Yeah, mic drop. Big old mic drop. 142, I did it. Questions? All right, then, I will look forward to seeing your presentations after break. Let me know if you need anything. I will be in touch with my feedback on your project check-ins. Enjoy your Thanksgivings. Woo.
Thank you.
See you on the other
I
side.
stand up trying to beat him.